Hi everyone, I'm going to present the work I've been doing in my PhD about model-based autoscaling for distributed data stream processing. Data stream processing applications are a de facto standard for real-time data analytics. These applications aim to process unbounded data streams with very low latency. They are usually represented as direct acyclic graphs, in which streams flow through so-called operators which carry out processing tasks. To keep up with high-volume data streams, DSP applications scale their execution on multiple distributed computing nodes. And for each operator in the applications, multiple instances can be run in order to process the incoming stream in parallel. Operator autoscaling, which is the subject of my doctoral work, is a key feature for DSP systems because they usually face highly variable workloads. DSP application autoscaling has been widely investigated in the literature in the last years. However, there are still some open issues that motivate my work. First of all, most of the existing solutions are either centralized approach, which can suffer from scalability issues in large-scale environments, or decentralized heuristics, like threshold-based policies, which are by nature unaware of application performance objectives. Moreover, existing solutions often assume that all the computing nodes in the system are homogeneous, which is not the case in modern fog-like environments. The first issue I considered in my research regards the control architecture to use for large-scale DSP systems. For this purpose, we defined a framework called EDF for hierarchical autoscaling control. EDF relies on the hierarchical MAPE control pattern for self-adaptive systems, where MAPE stands for Monitor, Analyze, Plan, and Execute. EDF comprises two components. For each application, an application manager supervises decentralized operator managers, which in turn control the autoscaling for single operators. These components work at different time scales and granularity of control to increase scalability. We then looked at the policies to be used within this framework. We aim to optimize multiple conflicting objectives, and in particular, resource usage, performance, in terms, for example, of processing latency, and the adaptation overhead, which is often significant for DSP systems. We formulated the autoscaling problem as a Markov decision process. An MDP is easy to solve when the system dynamics are completely known. However, we considered the case where the system model is not available. For example, the workload dynamics are not given in practice. So, we used reinforcement learning to solve the MDP and devise an optimal policy. In particular, we proposed a model-based reinforcement learning algorithm that exploits the available information about the system to speed up the agent learning phase. Then, we extended this solution to handle the presence of heterogeneous nodes, where we not only have to decide how many instances to run for each operator, but also the type of node to use. By doing so, we can balance, for example, performance, cost, energy consumption. The problem is that in this new context, the state space of our model explodes. So we had to combine reinforcement learning with function approximation techniques to compute a policy in a reasonable amount of time. We verified that our approach based on reinforcement learning is able to satisfy performance requirements while dealing with model uncertainty. EDF and the associated policies were implemented and evaluated on top of Apache Storm. There is also some ongoing work on the topic, which mainly involves the integration in a different framework, namely Apache Flink, and the integration of vertical operator scaling as a complementary adaptation mechanism. For future work, we plan to adapt our policies to to the case of DSP applications running on top of serverless platforms. Thanks for your attention.